So why is everyone, and I mean everyone, from Microsoft and Google to indie game developers, suddenly talking about a programming language named after, well, a fungus? What is the big deal with Rust? Let's get into it and figure out why developers consistently say it's the language they love the most.
You know, this quote right here, it gets straight to the point. For ages, developers have been haunted by these nightmare bugs, memory errors, that are just impossible to find and can open up huge security holes. And Rust comes along and says, hey, what if we could just make those impossible? But how on earth does it do that?
To really get Rust's magic, we have to go back in time and look at this fundamental choice that programmers have had to make for decades. It's always been a painful trade-off.
Okay, so on one side, you've got languages like C and C++. They are absolute speed demons. They give you raw, direct control over the hardware. But they also make you manage all the memory yourself. And if you make one tiny mistake, like a double free, where you accidentally release the same memory twice, your whole program can blow up or, even worse, silently start corrupting data. Then on the other side, you've got languages like Java or Go. They're much safer because they have this thing called a garbage collector that cleans up memory for you. The problem? The garbage collector can decide to run at literally any time, causing these sudden, unpredictable pauses. And for things like games or operating systems, that's a total deal breaker.
So you were stuck, right? You had to choose lightning fast but dangerous, or safe but sometimes sluggish. But what if you didn't have to choose? What if there was a third option that gave you the best of both worlds? Well, this is where Rust walks in with a completely revolutionary idea.
And this right here is Rust's superpower. It's a concept called ownership. The rule is actually pretty simple. Every single piece of data has one and only one owner. And the moment that owner is done with the data, boom, the memory is cleaned up. Instantly, automatically. And the key thing to get here is, this means you get all the benefits of automatic memory management, but without a garbage collector.
It's this system of ownership that stops those nasty bugs in their tracks. So look here. When we assign the value from user 1 over to user 2, we're not just making a copy. Ownership actually moves. From that exact moment, user 1 is no longer valid. It doesn't own anything. If you even try to use user 1 again, the compiler will literally stop you and say, nope, you can't do that. This one simple rule makes it physically impossible to have that double free error.
Okay, so wait a second. If only one variable can own a piece of data at a time, that brings up a pretty big question, right? How do you actually use that data in different parts of your program? It would be a total nightmare if you had to keep passing ownership around all the time.
And the answer is Rust's other stroke of genius, the borrow checker. Instead of giving ownership away, you can just temporarily lend it out. But the borrow checker enforces one incredibly powerful rule that prevents absolute chaos. Think of it this way. You can either have a bunch of people reading the data at once, or you can have one person writing to it. You can never, ever have both happening at the same time. This one rule single-handedly wipes out an entire class of nasty bugs called data races.
Let's see what this actually looks like. The code here seems pretty innocent in a lot of languages, right? We just grab a reference to the first item in our list of data, then we try to add a new item to that same list. Simple enough.
Now, in C++, this is a ticking time bomb. Adding a new element might force the whole list move to a new spot in memory, which would make our original reference point to garbage. It's a crash just waiting to happen. But in Rust, you don't get a crash. You get a conversation. The compiler stops you, it points to the exact lines of code causing the problem, and it explains why you can't be changing the list while you're still holding a reference to one of its items. It turns a potential disaster at runtime into a helpful learning moment before the program even runs.
So okay, we've got this unbelievable safety net that catches all these crazy bugs. But that has to come with a performance hit, right? I mean, that's the classic trade-off we were just talking about. Well, this is where Rust really truly changes the game.
The secret is something called zero-cost abstractions. It's a fancy term, but what it means is you can write really clean, elegant, high-level code and not pay a single bit of a performance penalty for it. You get the developer-friendly experience of a modern language, but with the raw, bare metal speed of C. Just take a look at this. It's so clean and readable. We're taking some numbers, filtering out just the even ones, squaring them, and then adding them all up. It's beautiful. But here is the absolute magic. The Rust compiler looks at this whole chain and boils it all down into one single, hyper-optimized loop of machine code that is often even faster than what a programmer might write by hand in C.
This table really shows what's going on under the hood. For just raw execution speed, yeah, Rust and C are neck and neck. But look at the difference under abstractions and parallelism. Because of Rust's super strict rules about ownership and borrowing, the compiler knows so much more about your code. It knows what's safe and what isn't, and that allows it to make much more aggressive optimizations that a C compiler just wouldn't dare to try.
So what's the final verdict here? When you combine this world-class, bulletproof safety with top-of-the-line performance, what do you get?
Well, the developer community has been shouting its answer pretty clearly for a while now.
For nearly a decade straight, Rust has been voted the single most loved programming language in major developer surveys. In 2024, it hit an 83% admiration score. That's not just a fad. It shows there's been a real shift in what developers are demanding from their tools. They want power, yes, but they also want safety and a good experience.
And it's not just love from individual developers, it's serious business. We're talking about the biggest companies on the planet. Microsoft is rewriting parts of the Windows kernel in Rust. Google is using it in Android and for the Linux kernel. AWS built some of its most important services with it. Even NASA is using it for flight software. And why are they all doing this? To completely eliminate entire categories of security bugs from their most critical code.
Now, let's be real. It's not perfect. There's a reason developers joke about their fight with the borrow checker. Rust's unique ideas create a learning curve that is, frankly, pretty steep. And because that compiler is working so hard for you, doing all those incredibly detailed safety checks, it can take longer to compile your code than with other languages.
But let's bring it all the way back to where we started. Microsoft has a statistic that says about 70% of their most critical security bugs are memory safety issues, the exact type of bug Rust is designed to prevent from ever existing. So the question I want to leave you with is this. If we have a tool that can wipe out the vast majority of our most dangerous software bugs before they're even written, is that steep learning curve worth it? Is this what the future of reliable, secure, high-performance software looks like?